everyone, this is Lakshmi from the Department of Data Science, semester 3rd, subject operating system, topic deadlock. Introduction to deadlock. Deadlock is a situation where two or more processes cannot be proceed because each is waiting for the other to release resource. It is significant issue in concurrent computing, particularly in operating system. Understanding deadlock is crucial for designing a robust system that can handle resource allocation effectively. Definition of deadlock. A deadlock occurs when a set of processes is blocked because each process is holding a resource and waiting for another resource. This results in cycle of dependencies that prevents any of the process from continuing. Deadlocks can lead to system inefficiency and require specific strategies for management and resolution. Conditions for deadlock. There are four necessary conditions for deadlock to occur: mutual exclusion, hold and wait, no, and crucial wait. Mutual exclusion means that at least one resource must be held in non shareable mode. Understanding these conditions is essential to implement deadlock prevention strategies. Mutual exclusion. Mutual exclusion ensures that only one process can use a resource at any given time. If another process requests that resource, it must wait until the resource is released. This condition is often inherent in resources such as printers, memory, and files. Hold and wait. Hold and wait refers to a process holding at least one resource while waiting to acquire additional resource. This condition can lead to situation where processes are waiting, identifying for resource held by others. Avoiding this condition is vital for deadlock prevention. No preemption. No preemption means that resource cannot be forcibly taken from a process, holding them until the resource is released voluntarily. This condition can create situation where processes are identifiably blocked. It makes resource management particularly challenging in multitasking environments. Circular wait. Circular wait is a condition where a set of processors are waiting for each other in a circular chain. This creates a scenario where each processor holds a resource needed by the next process in the chain. Breaking this chain is essential for resolving deadlock situation. Types of deadlock. Deadlock can be categorized into two types: resource deadlocks and communication deadlocks. Resource deadlocks involve processing waiting for resource, while communication deadlocks occurs in message passing system. Understanding these type can help in formulating appropriate solution. Deadlock detection. Deadlock detection involves identifying deadlock situations after they have occurred. Operating systems can use algorithms such as wait for graphs to detect deadlocks. Once detected, the system must take step to recover from the deadlock. Deadlock prevention. Deadlock prevention aims to ensure that at least one of the necessary conditions for deadlock cannot be held. Strategies include enforcing mutual exclusion, eliminating hold and wait, allowing preemption, and avoiding circular waits. Prevention techniques can significantly enhance system reliability and performance. Deadlock avoidance. Deadlock avoidance is a more dynamic approach than prevention, allowing research to be allocated only if it is safe to do so. The banker's algorithms is a well-known deadlocks avoidance strategy used in resource allocation. This technique assesses the system's state before granting resource request. Deadlock recovery. Deadlock recovery involves taking action after a deadlock has been detected. Common recovery methods include process termination and resource preemption. The goal is to restore the system to a normal operational state as quickly as possible. Process termination. One way to recover from deadlock is to terminate one or more process involved in the deadlock. This can be done based on priority or resource usage. Terminating process may lead to loss of data and requires careful consideration. Resource preemption. Resource preemption involves forcibly taking the resource from one or more process. This strategy can resolve deadlocks but may lead to inconsistency or data corruption. It requires careful management to ensure that the system remains stable. Deadlock in real world system. Deadlock situation commonly occurs in database management system and operating system. For example, multiple transactions might hold locks on a resource while waiting for each other. Recognizing deadlock scenario in real world applications is crucial for system administration. The 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 philosopher problem is a classic problem illustrating deadlock. In this scenario, philosophers must pick up frogs, but they can end up in a deadlock situation of if each holds can of one frog. If it highlights the need for effective resource management in concurrent systems. Tools for deadlock detection. There are various tools and algorithms available for deadlocks detection in operating system. Example include wait for graphs, resource allocation graphs, and detection algorithms. These tools are essentials for maintaining system and performance. Best practice for deadlock management. Implementing best practice can help in the risk of deadlock occurrence. Techniques include limiting resource allocation, using timeouts, and prioritizing requests. Regular system audits and monitoring can also aid in identifying and resolving potential deadlocks. Further of deadlock management, as system evolve, new methods for managing deadlock are being researched and developed. Advances in artificial intelligence and machine learning may offer predictive capabilities for deadlock management. Continuous improvement in resource allocation strategies will enhance system reliability. Conclusion. Deadlock is a